which is a May, June 2022 41 variant question. Question number 3. A fixed mass of an ideal gas is initially at a temperature of 17 degrees Celsius. The gas has a volume of 0.24 meter cube and a pressure of 1.2 times 10 power 5 Pascal. In A part 1, which carry 2 marks, we need to state what is meant by an ideal gas. To do this question, we need to know what is an ideal gas. An ideal gas is a gas that obeys PV proportional to T. Or you can say PV is equal to nRT, where P is the pressure of the gas, V is the volume of the gas, and T is the thermodynamic temperature. This is how you get the 2 marks. Then for part 2, we have to calculate the quantity of gas. First, this question also carries 2 marks. First, we change the temperature in degrees Celsius to temperature in Kelvin by using this formula. And then after that, we use PV equals nRT to calculate the N, which will give you 12 moles. So substituting the pressure, the volume, and the temperature of the gas into the equation. Part B. The gas undergoes 3 successive changes as shown in figure 3.1. The initial state is represented by point A. The gas is cooled at constant pressure to point B, from A to B by cooling. By the removal of 48 kilojoule of thermal energy, that's why your Q is minus sign, because heat energy is removed from the system. The gas is then heated at constant volume to point C. So from B to C, the gas is heated. Finally, the gas expands at constant temperature back to its original pressure and volume at point A. So the gas goes back to A. During this expansion, the gas does 31.6 kilojoule of work. For part 1, we need to show that the magnitude of the work done during the change AB is 19.2 kilojoule. We know that the volume of the gas decreases from 0.24 meter cube at A to 0.08 meter cube at B. The gas is compressed and therefore work is done on the gas. W is positive. To get the 2 marks here, the first mark is a formula. Work done equals to P times delta V. The pressure is 1.2 times 10 power 5. And then 0.24 minus 0.08 is the change of volume. This will give you the second mark, which is 19,200 joule or 19.2 kilojoule. Then for part 2, complete table 3.1 to show the work done on the gas, the thermal energy supplied to the gas, and the increase in internal energy of the gas for each of the changes AB, BC, and CA. The numbers here 1, 2, 3, 4, 5, 6, 7, and 8 represent the sequence of thinking. And then this question carries 5 marks. The first mark is to put positive 19.2 kilojoule here. This is because work is done on the gas. Energy is given to the gas. Then the second mark is to calculate using your new thermodynamic first law to calculate minus 28.8. Your delta U is unknown. Your Q is minus 48. And then your W is positive 19.2. This will give you minus 28.8. This will give you the second mark. So 1 mark here, 1 mark here, 2 marks already. And then the third mark is here. The work done for the gas for BC is 0 because there's no change in volume. The volume is constant. So delta V is 0, so work done is 0. So this will carry another mark. So together 3 marks now. And then since the gas from C to A expand at constant temperature, we know that this is an ideal gas. For an ideal gas, the internal energy is due to the random distribution of kinetic energy, which is proportional to temperature in Kelvin. The potential energy is 0. So since the temperature is constant, there's no change in internal energy here. This is why this value is 0. And when the gas return from C back to A, return to A at the same temperature, pressure, and volume, there's no change in internal energy for this cycle. A, B to C, then to A. There's no change in internal energy. Therefore, the change in internal energy for AB plus the change in internal energy for BC plus the change in internal energy for CA equals to 0. Now we know that the change in internal energy for AB is minus 28.8. And we know that the change in internal energy for CA is 0 because the gas expands at constant temperature. Temperature is constant, therefore the internal energy no change. Therefore, you can find your delta U BC, the change in energy for BC, which is 28.8. So this will be 1 mark, 1 mark, 1 mark. These two will be 1 mark. Number 7, 8 will be 1 mark. Then 7, 5, and 6 will be 1 mark. To get number 6, we use thermodynamic first law, delta U equals to Q plus W. Your delta U is 0. Q we don't know. And then your W is 31.6. This will give you Q equals to 31.6. These two will carry 1 mark. And then for this 28.8, for number 8, we also use thermodynamic first law to calculate. So delta U equals to Q plus W again. So delta U is 28.8. Your Q is unknown at the moment. Your W is 0. So your Q equals to your delta U, which is 28.8. This will carry another mark. And then this is a reasoning for how to get the marks here in the question. This is a summary of the concepts and ideas needed to solve this question. First, we must define an ideal gas. Number 2, you must be able to convert temperature from degrees Celsius to Kelvin. Then number 3, you must use PV equals nRT to calculate your N. Then number 4 is to calculate the work done on or by a gas using the formula work done equals to P times delta V. W is positive when work is done on the gas. This happens when the gas is compressed. W is negative when work is done by the gas. This happens when the gas expands. Number 5, state and use the first law of thermodynamics. Your delta U equals to Q plus W. Where your U represents the internal energy, your W represents the work done on or by the gas, and your Q is the thermal energy or heat energy absorbed or removed from the system. Then you need to know the internal energy of an ideal gas is only due to the random kinetic energy. The random potential energy is 0. The kinetic energy is proportional to the thermodynamic temperature.